Okay, so we are going to do a location shift problem. Location shift, that's meaning shift in location. Key difference between chapter 3 and chapter 4 is here we have independence. So last time we looked at hard data in the sense X was connected to Y in some way. Here, X and Y are independent, two separate samples. So we're not doing before minus after. Sure, I can call it as before minus after, but it needn't be from the same person, right? You can call it treatment versus control, but it needn't be from the same person or same subject. So two separate samples, the parametric equivalent of this test a two sample t-test. So you have two samples and you want to say how they differ in terms of average. Here, as always, non-parametric tests, we don't necessarily need a parameter, but typically people would go for the median, which will be the mean. But you don't have to make assumptions about distributions and such. So why do we call it a location shift test? Suppose I define delta, delta typically is denoted for change, as y minus x. Yes, if y is equal to x, then what is delta? That's an easy question. Do 0. If y is greater than x, then delta would be greater than 0. If y is less than x, then delta would be less than 0. Agreed? No. If y and x are the same, you are in the same location. Do you agree? Let's say x is over here and I move a tiny bit. So y greater than x, right? Our objective in this test is to verify if the move that I made is significant or not. Good. That is the fundamental concept of statistics. Just because something is greater doesn't make it greater. In a similar manner, if that is x, and if I move to the left, I'm saying there is a shift in location. Agreed. So the corresponding test that we have here, what type of test would it be? Would it be right tail, left tail, two-tailed? Two-tailed. You're testing for the change equal to 0 against change not equal to 0. So if you, of course, once you get a two-tailed test, you can do a post-hoc verification and come to a conclusion about those. Here, delta is 0 against delta greater than 0. Yes. Last case, delta equals 0 against delta less than 0. Good. The very first test that we are going to do is a Wilcoxon rank sum test. Wilcoxon sign rank was used for paired data. X and Y are dependent. Same scenario, Wilcoxon rank some independent samples. Just like a two-sample t-test in the parametric inference, you would have a two-sample t-test where you have paired data. If you Google t-test, you will see a t-test for independent samples, a t-test for paired data. Similar manner, Wilcoxon's sign rank test is for paired data, dependent samples. Ransom, on the other hand, independent samples. Good. So let's say we have a sample of X values. Have sample X has M observations, sample Y, N observations. Now, let me just start with the simple example. Let's say good. How many X observations do I have? 5.
You missed
I missed 4. How much? 5. 4. 6. And Y observations, Y1, Y2, Y3, 3. Let's say this is sorted. Let's say this is not sorted. And once we sort, we have these runs. Good. So original observations, I'm just going to sort them. Once I sort it, these are the ranks that I get. Yes, no, maybe. In total, I have 9 observations. If I combine X and Y, so I have 9 ranks. Good so far? Yes? What is the sum of all ranks? Nine times 9 plus 1 over 2. Yes? So 9 multiplied by 10 divided by 2, we get 45. Yes? Based on my definition in the simple sample that I chose, M is, what is M? I'll let you tell me. What is M? Based on the way I've defined it.
Number of your X.
Come again.
Are you?
See.
I defined sample 1 as x1 through xm, sample 2 y1 through yn. I'm giving you this sample. I want to know what n is. It's 6. What is n? 3. So I can write that 9 as n plus n. Correct. We will get to this later. So that is the total sum. And look at that sample. I didn't even give you numbers, did I? I did. I just wrote abstract X's and Y's, but I did tell you the rank. Once you sort, these are the positions of each of the observations. Look at the rank and tell me if the y values would be bigger than x before that. We call it Wilcoxon because found by Wilcoxon. Rank. What is the next rational thing to do? Sum, right? So if I sum all the x ranks and sum all the y ranks, which is going to be bigger? X ranks, right? So if the ranks of x are bigger, the x values are moving farther and farther away from y. Do you agree? Correct? So if you conclude that the y value is relatively small, then we can conclude that y is less than x. Yes? Which would mean delta is less than 0. Does that make sense? So in this case, I can partition the sum, the total sum, I'll put, these are not the x values, these are the ranks. If I sum all the x ranks, I would get 1 plus 3 plus 5 plus 7 plus 8 plus 9, 33. Naturally, what should the y ranks be? Huh?
So the others. 2, 4, 6.
Okay, another way of.
Oh, or you 45 minus.
45 minus 36. You can sum the others. It is the same as saying 45 minus 33. We will get 12. Yes? So if the sum of x is significantly bigger than the rank sum of y, then we can conclude that x is significantly bigger than y. Do you agree? Likewise, if the sum of y is significantly bigger than x, we can conclude that sum of y is bigger than sum of x. Correct? So that is all we're trying to do. Key observation. In doing this, we are combining the samples together before we assign the ranks. We have two different sums. We have to make up our mind and pick one. Should we base our test on x ranks? Should we base it on y ranks? Or does it really matter? Huh?
Well, I mean, you should base it on X, but probably doesn't matter.
Nothing really matters, right? Metallica song. So it doesn't matter because you have only two things, and if you base your conclusion on this sum, that implies this. If you base your conclusion on this one, I can conclude something about that. So it really doesn't matter. Your book uses y. So W is what we call the Wilcoxon rank sum. Mind you, when I put that subscript I over there, I'm not saying I'm going to take the value of y, I'm rather taking the rank of y. Good? So that is the rank of observation yi. I forget what notation your book uses, but this is standard notation. Good. So that W is the Wilcoxon rank sum statistic. Now we just have to write it for 3 different tests. Very first test. Delta equals 0 versus delta not equal to 0. Good. 210. Rejection region on the right, rejection region on the left. Critical value, I'll call it W alpha over 2 plus, 1 on the right side, W alpha over 2 minus, left hand side. Why do we have alpha over 2 and not alpha? This is a two-tone test. Good. Suppose I found this critical value, right? How would I find that critical value? How did we do this with sine law?
The total sum.
We used that total sum and then subtracted it. If we knew t plus, we can find t minus using the total sum. T minus, we can find t plus using the total sum. We're going to use a similar logic here. The total sum m plus n multiplied by n plus m plus 1 divided by 2, or n plus n, one of the same. Do we agree? Yes. I can partition this as I can distribute the m and n. I can write it as m multiplied by n plus m plus 1 over 2. Yes. Plus n multiplied by n plus m plus 1 over 2. Good. So what do we have in common? N plus m plus 1. And we'll go back to that. Let's not do that. So if you look at these two, you can see this is part of the total sum. That is part of the total sum. This would correspond to the sum of y rank, sum of x ranks. Under the null, this is what happens. So under null, m would equal n. The derivation. So if you put those two together, you'd end up getting 2n n plus m plus 1 over 2. Agreed? This would become n over 2, n over 2, 2n over 2.
But the n is also changed to.
You should. Well, let me see. Weird way of putting it, I shouldn't say n equals m. So under the null, the way the derivation works out is these two will become the same, but that wouldn't change. And if you cancel those, it will reduce to n times n plus m plus 1. The huge derivation in the paper, we're not going to do. So that would be the sum, net sum that we have. Now that I've given you this, what would be W alpha over 2 minus in terms of W alpha over 2 plus?
Yeah.
Huh?
But-
So,
Times n plus 1 plus 1. N plus n.
so this side would simply be n times n plus m plus 1 minus that. Yes, just like t plus t minus equals total sum t, same argument. W alpha over 2 minus W alpha over 2 plus, you would get n times n plus 1 minus alpha over 2 on the other side, you will get this. If you find this, just change that to minus, you'll get that. You have symmetry. On the right hand side, if you want to do a right tail test, I don't have two rejection regions, rather I'll have only one, and where should it be? Will be on the right hand side. And we will denote it as W alpha plus. I use that subscript alpha notation because we base the critical value off of the level of confidence. Oh no. In a similar manner, if we take a left tail test, delta equals 0 against delta less than 0, correct? Where would the rejection region be? Left hand side. We will denote it as W sub alpha minus 1. Not minus 1, raised. Now, the W critical values, they are all obtained from a distribution. Last time it was the Wilcoxon sign rank distribution. This is simply the Wilcoxon rank sum distribution. So in R, we shouldn't be using Q sign rank, P sign rank, like we did last time. This time, we would use P Wilcox, Q Wilcox. I'll show you how. Of course, I'll give you the tables for the critical values, but not the P values. Wilcoxon tables. Good. So to get these, you need R. To get the P values, we need R. I'll generate a table for you to do it manually, but we can only do the critical method. If I have to do a large sample approximation, I have to standardize W. Agreed? That's exactly what we've been doing. With the binomial test, we had B, we subtracted the mean mu divided by sigma, standardized it. It became what distribution? No. And then we moved on to Wilcoxon sign rank test. I had T plus. Large sample approximation, I subtracted the mean divided by the standard deviation, ended up getting the standardized test statistic, had a normal distribution. You should know where I'm going with this. And then came Fisher sign test. I had T minus mu divided by sigma. It became standard normal distribution. Same thing. So if I have W minus mu divided by sigma, what would it have? It'll be a standard normal. So the standardized test statistic W minus mu divided by sigma under the norm will be standard normal. Oh, tilde means distributed by. Yes.
Why do we use the Z distribution for binomial large approximation?
We're not using it directly for binomial. We are actually using it for B minus the mean divided by standard deviation. So generally speaking, if you increase the sample large enough, even the binomial would approach a norm in large sample sense, center limit theorem. Pretty much every distribution, sample is large enough, it will approach normal distribution.
But doesn't Z distribution require the population standard deviation?
No. That's, so when I subtract mu and sigma, I'm actually subtracting the actual theoretical mean by the theoretical standard deviation. Well, in a sense, going back to 2023, that theoretical standard deviation is the population standard deviation. By all means, when we say population mean, population standard deviation, in my mind, all they are talking about is the theoretical mean and the theoretical standard deviation, or the actual value of what you get from the sample. We just call it population to make things easier. Does that make sense? Sort of. So W minus mu divided by sigma will be a normal distribution in a large sample sense. But we have to subtract the mean of W, in other words, the expectation of W, the theoretical mean of W, U. Variance of W. Here is a question. I won't do the derivation for the variance. Want to keep things simple in this class because not everyone knows expectation, variance, all that stuff. So this is easy. You should be able to tell me what mu should be. I've given you from earlier under the null distribution of W will follow Wilcoxon's sign rank. The maximum range that the total sum that it could have is n times n plus m plus 1. Yes? If that is the case, what would the mean of W be? The total range is 0 through n times n plus m plus 1. Clear? Just divide by Paul
Well, like the amount of like that.
By 2.
by 2. You divide it by 2. So if you have sum of 0, 1, 2, dot, 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 goes all the way up to n times n plus 1 plus m, n plus m plus 1. And I ask you, well, where do you think the middle would be? What would your answer be?
Divide by 2.
Divide that by 2, right? So the mean mu is simply n times n plus m plus 1 divided by 2. Variance, on the other hand, requires a derivation. Mn multiplied by n plus m plus 1 divided by 12. Yes. Go ahead.
For your mu, didn't you derive the n times n plus m plus 1 only for the 2 tau test?
What do you mean?
Doesn't it only apply to the 2 tau
Mm-mm.
test?
This is the total sum that I would have under the north. In other words, W could go all the way from 0, and that would be the maximum value that W can take. So this is the sum, maximum sum that W could have under the null distribution. What is the null distribution? The null is that delta is equal to 0. Yes.
Why 12?
Huh?
Why 12?
Why did we have 12 with
Oh,
sign rank?
One, okay.
No, with sign rank, we had 12 because n times n plus 1 times 2n plus 1 divided by 12 is the sum of squares of natural numbers. If you have n natural numbers, you square them, then you add them, you'd have n times n plus 1 times 2n plus 1 over 12. Same logic. If you put it in the variance formula, you'd have to find expectation of w squared. So you will get a 12 there. You take a common denominator and you subtract and simplify, you'd end up with this. So have mu, I have sigma squared. I can simply find the test statistic, say, standardized test statistic. Does that make sense? So the key is to first find W. Once we find W, we can use W to reject, not reject, depending on the test. When we get to the large sample approximation, we want to find the standardized test statistic. We have to subtract the mean of W, theoretical mean, which would be that, and theoretical variance will be that. Good. There is another formula which we will use under ties or when there are ties. I'll save that for later.